In Newtonian physics, the structure of space does not change, regardless of what physical phenomenon occurs in it. Therefore, absolute time and space exist independently of any perceiver. According to Einstein's theory of general relativity, however, massive bodies cause a curvature of spacetime. Consequently, absolute time does not exist, and bodies change the space around themselves. Massive accelerating or orbiting bodies cause ripples in spacetime which travel at the speed of light. These are called gravitational waves. When a gravitational wave passes through a certain point in space, it causes lengths there to shorten for a very short time, then to lengthen. These changes are very small. It was impossible to detect them before LIGO. The strongest gravitational waves are formed when black holes merge. When this occurs, the energy released in the form of gravitational waves is enormous. It is the most intense release of energy in the universe known to science so far. LIGO's measuring instruments are so sensitive that they can detect even the weakest terrestrial vibrations, which may be caused by earthquakes, ocean waves crashing on shores, explosions, and so forth. Therefore, in order to distinguish true cosmic signals from terrestrial noises, it is necessary to compare the signals detected by several observatories located thousands of kilometers apart. Initially, there were only 2 LIGO observatories, one in Louisiana, the other in Washington State. Then, in 2017, the Virgo Observatory in Italy joined the LIGO project too. The central building houses the most important parts of the observatory: the laser unit, mirrors, detectors, and computers for processing signals. There are 2 4-kilometer-long arms perpendicular to each other, extending from the central building, encasing 2 vacuum tubes in which the laser beams travel. At the end of each tube, there is a mirror. The operation of LIGO is based on the fact that lengths change for a brief moment when a gravitational wave passes through a point in space. Lengths stretch in one direction and shrink in the other direction. The change in the lengths of the 2 arms of LIGO is measured with an interferometer. During its operation, a laser beam is split into 2 identical beams by a semi-transparent mirror. The 2 beams travel down the 2 perpendicular arms. When they reach the mirrors at the ends of the arms, they are reflected back towards the splitter mirror, where they merge into a single beam. Depending on the difference between the paths the 2 beams travel, they either intensify or weaken each other. This method can be used to show path length differences that are in the range of the wavelength of light. The longer the path the light beams travel, the greater the sensitivity of the instrument. A gravitational wave passing through the 4-kilometer-long arms of the observatory changes their length only by 1,000th of the diameter of a proton, but the instrument is able to detect even this small change. The LIGO's first verified detection took place on the 14th of September 2015. The signals it detected were emitted during the merger of 2 black holes with 36 and 29 times the mass of our Sun, respectively. The detection lasted only 0.2 seconds. The signals clearly showed how the intensity and the frequency of the gravitational waves increased as the 2 black holes orbited each other with a gradually shortening radius until eventually they merged and the signals faded. By comparing the strength of the detected signals and the predicted signals, scientists were able to estimate that the distance of the source of the waves was about 1.4 billion light-years. That is, the event detected by the instrument occurred about 1.4 billion years ago, and its gravitational waves reached the Earth only now.